Hello and welcome again to our calculus course. I think you're really going to enjoy today's lecture because we're going to put a lot of ideas together. All those ideas we studied about the first and second derivative, plus some pre-calculus skills like symmetry and intercepts, we're going to put them all together to study how to graph curves, how to actually graph a function. And we'll see that the skills are kind of, it's almost overwhelming because we have so many tools now to discover where the graph is increasing, where it's concave, upwards, etc. This is not an exact science. Graphing functions is difficult, and you have to sometimes do a preliminary graph and then correct it, and etc. But we'll go through a couple of examples to give you an idea of how I think about graphs, and then you'll be able to practice some in the workbook. And near the end of the lecture, we'll talk about something called linear approximations. Basically, that's using the tangent line to a curve to approximate that curve. So let's begin, as I always do, with a nice example to see about what kind of skills come into play when you graph a function. And this is a fairly complicated function. It's 2 times x squared minus 9 over x squared minus 4. Again, I'm not going to calculate the derivatives. I'll just give them to you. I trust that you could do these calculations if you had some free time. But let's start talking now about what we know about the curve, given this information about the function and its 2 derivatives. Well, let's step through some ideas. What about the intercepts? Look back at the function. If x is 3 or minus 3, f of x is 0. So those are intercepts, 3, 0, and minus 3, 0. And if x is 0, we get that y is 9 halves, and that is also an intercept, 0, 9 halves. How about symmetry? Oh, it's x squared in the numerator and denominator. It's going to be an even function, symmetric about the y-axis. How about asymptotes? Remember asymptotes? Well, it's got an x squared minus 4 in the denominator, so 2 and minus 2 are not roots to the numerator, so those are vertical asymptotes at x equals 2 and minus 2. And there's also a horizontal asymptote, because this is a polynomial of degree 2 divided by a polynomial of degree 2, so the quotient of leading coefficients is 2. So y equals 2 is a horizontal asymptote. Step down to the first derivative. Are there any critical numbers? Well, 0 is a critical number because that makes the numerator 0, but be careful, 2 and minus 2 are not critical numbers. Those are the asymptotes. They are not in the domain, are they? There's only one critical number, and it's actually one of the intercepts, 0, 9 halves. So what I suggest at this stage is draw a preliminary graph. Here I've indicated 2 vertical asymptotes at 2 and minus 2, a horizontal asymptote at y equals 2, the intercepts at 3, 0, minus 3, 0, and then up on the y-axis at 0, 9 halves. Somehow our graph has to sort of fit into this picture. Well, we haven't used much calculus yet. Let's now analyze the first and second derivative using this argument of test intervals. So the first derivative, we'll draw our little number line, and the key points are minus 2, 0, and 2. I admit minus 2 and 2 are not critical numbers, but the increasing, decreasing nature of the function could change there, even though they are not critical numbers. So we should look at those numbers. So let's start analyzing these intervals. If x is bigger than 2, the first derivative, of course, is then positive. And as I cross 2, the first derivative stays positive because that denominator is squared. It's only when I cross 0 that the first derivative changes to negative. So my conclusion of the first derivative is it decreases from minus infinity to minus 2. It then hits the vertical asymptote, and it continues to decrease from minus 2 to 0. And then you reflect it over by the symmetry, and you get that it increases from 0 to 2, hits the asymptote, and increases again from 2 to infinity. How about concavity? Let's look at the second derivative. The key points here are -2 and 2 because that's when the denominator vanishes. Again, those points are not in the domain, but those are the vertical asymptotes. The numerator is always negative, isn't it? So that's not going to be a problem. So what happens to the right of 2, a large positive number? You would get that the numerator is negative and the denominator is positive. So f double prime is negative there. It's concave down. And similarly, you would analyze the signs change. It's concave down, concave up, concave up, concave down. Notice as I cross 0, the concavity does not change because 0 is not important in the second derivative. It was really only important in the analysis of the first derivative. So let's put this all together. And this is hard to do. You have to sort of sketch the graph as you're going along. I know it's decreasing, but it's got a horizontal asymptote at y equals 2. And the function then decreases. It crosses the intercept at -3 and then goes down and hugs its vertical asymptote. And then you jump up and it starts at +infinity and it decreases down to that intercept and critical number 0.9 halves and then increases again, and you see that it's concave up on the interval -2 to 2 and then similarly the right hand piece. So you put all these together, the increasing, decreasing nature, the concavity issues, and you obtain this final graph. It's not an easy skill to graph. It takes some time. And of course you can verify this with the graphing utility, but in a minute I'll show you how that can be misleading. So let's summarize some of the techniques that come into play when you want to graph a function. As I said earlier, it's not an exact science. We have lots of tools to use: intercepts, symmetry, domain consideration, asymptotes, and then we can look at derivatives. First and second derivative to find out where the relative extrema are, concavity, inflection points, etc. I always recommend you do some point plotting. Put in a few points just to get a feel for the graph. And again, graphing utilities can be very useful here to verify the graph you produce by hand. That said, let me show you how misleading graphing utilities can become. I've had students tell me, like, Professor Edwards, why do we spend time learning how to graph functions when I can just plug it into my calculator and the graph appears in front of me? Well, it's not clear how you plug it into your calculator the correct way. For instance, suppose in that previous example I made it a little more complicated. And in real life, most functions are much more complicated than this. I'm going to add a factor in the numerator and denominator, x minus 20 over x minus 21. And now I'm going to graph it as most of us would on the standard screen, minus 10 to 10, minus 10 to 10. And here's the picture of my new function. Well, that kind of looks like the old function, doesn't it? And if you were to put that down as your answer to the graph of that second function, the larger function, you'd be wrong, because that second function has some features past 10 and past minus 10. And you only discover that it has those features if you use calculus. In other words, you have to pick the correct viewing screen to capture all the important features of the graph. Let me show you the graph of this fatter function down here on a different viewing screen. Wow! There's some other things happening on this graph way out near 30. It's not so obvious. This graph does not look like the other one. So you really need to know some calculus to find those points where interesting things are happening. Like out there near 30, some weird stuff is happening. There's another vertical asymptote out there, isn't there? Okay, so that said, I hope I've convinced you that we really do have to spend some time getting our hands dirty doing some of these graphs. Good. Let's look at another example. I think you'll like this example because it has some very challenging pre-calculus skills that go along with this example, and I'm going to spend some time on those pre-calculus skills in a moment. But let's first do the calculus portion. Let's consider the function 2x to the 5/3 minus 5x to the 4/3. This function has a domain of all values of x. You can take the cube root of any real number. So we have no domain issues. There are the first and second derivatives. And in a minute, I'll show you how I got the factored form of that first derivative, because that's a non-trivial calculus skill. I think you're very good at differentiating f of x, and you'd get an answer, but it would be the difference of two terms. I've written the first derivative factored. I'll show you how to do that in a moment. And then there's the second derivative as well, and it again is factored. Okay, what can we say about this function? Let's think about it. Any intercepts? Well, look at the original function. If x is 0, then f of 0 is 0. And there's another intercept. It turns out that when x is 125/8, you get an intercept. Wow, that's hard to get. And I'll show you in a moment, just trust me for the time being, that that is the second x-intercept. I'll show you in a moment how I got that. Again, it's some tough pre-calculus. Are there any asymptotes? Well, no. Asymptotes usually occur when you have a quotient, and here we just have a function just straight across. There are no vertical or horizontal asymptotes. How about critical numbers? Well, we look now at the first derivative. And is it ever 0? Yeah, when x is 0, it's 0. And when x to the 1/3 minus 2 equals 0, what does that mean? That means that x is 8. The cube root of 8 is 2. So we have two critical numbers, 0 and 8. Let me evaluate the function at those critical numbers. F of 0 is 0. That's easy. F of 8 turns out to be minus 16. That's not so easy, is it? If you plug in 8 into that expression for the function, let me show you how you evaluate it. 8 to the 1/3 is 2. 2 to the 5th is 32. And 2 times 32 is 64. Remember 64. Now I'll do the second term. Cube root of 8 is 2. 2 to the 4th is 16. 5 times 16 is 80. So it's 64 minus 80 minus 16. Ouch. That's tough. That's tough stuff, isn't it? It's not calculus. It's not calculus at all. But it's very difficult. I'm the first to admit it. It's not easy for me to do it either. Okay, on to the second derivative. Are there any inflection points here possibly? Well, look at the expression for the second derivative. The numerator is 0 if x is 1, and the denominator is 0 if x is 0. So those two x values, 0 and 1, are potentially inflection points, and the corresponding y values are 0, 0, and 1 minus 3. So let's do again a preliminary graph putting in some of these early features that we identified. 0, 0, 8 minus 16, 15.625, and then 1 minus 3. The two intercepts are at 0 and the 15.625, and then we have the 8 minus 16 and the 1 minus 3 as the possible critical number and a possible inflection point. Good. That's not the graph, obviously. We have some more work to do, don't we? But at least we have a piece of the graph. We have some information without doing much thinking. On we go. Let's analyze the first and second derivative using our little number lines. Okay, so let's start with the first derivative. And what are the key values here we have to mark on our number line? We have to mark 0 and 8 because that's where it potentially changes sign. If x is bigger than 8, then the first derivative is positive. If x is between 0 and 8, it's negative. And if x is below 0, less than 0, it's positive again because it's a negative times a negative. So we go from increasing, decreasing, increasing. Good. By the first derivative test, we now know there's a relative maximum at 0, 0, because it increases up to 0, 0, and then it decreases. That's a relative maximum. And similarly, there's a relative minimum when x is 8, and that's the point 8 minus 16. Good. How about our inflection points? Well, let's look at the second derivative, which will tell us about concavity and inflection points. The second derivative says that when x is bigger than 1, it's positive. So I'll put little plus signs for x bigger than 1. Between 0 and 1, the second derivative is now negative. But watch what happens when I cross 0. It stays negative. Why is that? Well, at 0, we're dealing with x to the 2/3, aren't we? That's something squared. So it's not going to change sign when I cross x equals 0. So it's concave down from minus infinity to 0, concave down from 0 to 1, and then concave up from 1 to infinity. And clearly x equals 1 is an inflection point because the concavity changes. So let's put all this together. Wow, there's a lot of information here, isn't there? But here is the ultimate graph, and this is how we think about it. It was increasing up to 0, 0, and then decreasing, and that was a relative maximum at the origin. Then it was decreasing down to 8 minus 16, where we have a relative minimum. And notice that on the way, the concavity changed. It was concave down for a while, and then it's suddenly concave up. When x is 1, we get a point of inflection. And it stays concave up forever, and it crosses the other intercept at 15.625. Tough going, lots of stuff. The graph's actually kind of simple looking, isn't it? But it took a little bit of work to get it. Now, I promised to go back and look at some of the pre-calculus skills that I kind of sloughed over there and kind of went blah, blah, blah. Now I'm going to get my hands dirty here with some pre-calculus. The bottom line is factoring can be difficult in mathematics. This is true all through mathematics, but we need to do it. I pointed out that we had an intercept at 125 over 8, which is that 15.625 number. Let's see how I got that. The original function was 2x to the 5/3 minus 5x to the 4/3. I want to know where that function equals 0. That would give me the intercepts. Well, let's factor out x to the 4/3, the largest power of x to the 4/3. And when I do that, I'm left with 2x to the 1/3 minus 5 inside the parentheses. You can check that by multiplying x to the 4/3 through the parentheses, and you'll get the original expression. Okay, so that product equals 0. That means x is 0, or that second term is 0, which is 2x to the 1/3 minus 5. So let's solve that equation. 2x to the 1/3 equals 5, or x equals 5/2 all cubed. And 5/2 cubed is 125 over 8. Again, pretty rough going, wasn't it? Another issue that came up in this problem that I kind of left to the side was how I factored that first derivative. So remember, we had our function 2x to the 5/3 minus 5x to the 4/3, and I said, well, anybody can take the derivative. That's pretty easy. The derivative would be 10/3 x to the 2/3 minus 20 over 3 x to the 1/3. That's just using the power rule twice. But now I want to factor that because I want to know where the derivative equals 0. And that requires putting it in factored form. Well, first factor out the 10/3. Get rid of that constant. And you're left with x to the 2/3 minus 2x to the 1/3. And now factor out x to the 1/3. And look what happens. You have 10/3 times x to the 1/3 times the quantity x to the 1/3 minus 2, which is what I showed you on a previous slide. Now it's easy to tell when the derivative is 0. I had the two factors. Either x is 0 or x to the 1/3 is equal to 2, which makes x equal to 8. Good. That was kind of some rough pre-calculus, but I hope you sort of found it kind of interesting how it had a very important role in finding the graph of that function. Well, let me turn to a different topic now. This topic is somewhat fading away in the calculus curriculum. And one reason is it has some pretty unpleasant notation. But the principle of this topic is going to be with us forever. So the underlying idea here for the next 10 minutes or so, keep this in mind. The tangent line to a curve is a good approximation to that curve near the point of tangency. That is the underlying idea throughout this so-called linear approximation topic that we're now going to talk about. So remember that back in lecture 1, we talked about the tangent line to the curve y equals x squared at the point 2, 4. And we pointed out that that tangent line touches the curve once, and it's very close to the curve nearby the point of tangency. That's the core of what we're about to talk about. In many applications in mathematics, scientists assume that the function they're dealing with is locally equal to its tangent line. They call that linearization. Assume your model is linear. That's because in a lot of cases, functions are too complicated. So they kind of assume that locally, near the point they're interested in, the function is really equal to its tangent line. Physics majors know this when they study pendulums that are swinging. So linearization is what we're talking about now. Let me first do a fairly simple example of the tangent line approximation to a curve. This will be very easy for us because we've done things like this before. Let's find the tangent line approximation at the point 0, 1 to the curve f of x equals 1 plus 2 sine x. This is a lot of big words asking for the following. What's the equation of the tangent line to that curve? That's what we're asking here. We're just using different words for the same idea. We're calling it the tangent line approximation. It's the tangent line to that curve. How do we do it? Well, you remember. Take the derivative. The derivative is 2 cosine. Plug in the value 0 into the derivative, and you get that f prime of 0 is 2, because cosine of 0 is 1. And now form the equation of the tangent line. Using the point slope formula, you get y minus f of 0 equals f prime of 0, the slope, times x minus 0. F of 0 is 1, so you get y minus 1 is 2 times x minus 0, and then simplify y equals 1 plus 2x. Let me show you a picture of this. There's the original curve, which was 1 plus 2 sine x. It kind of looks like the sine curve, doesn't it? And there's the tangent line. And I think we all believe that near that point of tangency, the tangent line and the curve are very close together. Let me convince you by picking a value close to 0. How about 0.1? F of 0.1 would be 1 plus 2 sine 0.1, and that turns out to be 1.19967 approximately, using my calculator. What's the tangent line at 0.1? Well, that's much easier to calculate. It's plug it into the tangent line, 1 plus 2 times 0.1, that's just 1.2. And lo and behold, look, those two numbers are very close together. Okay? That's what we're after. Well, I think the idea is pretty simple, but now we put a lot of symbols into play here that sort of make things a little bit uglier. But there's some symbols here that actually will keep playing a role in our calculus course, especially when we get to a topic called integration. So I feel obliged to present these ideas, and I think you'll be able to follow them. So here we go. Recall that the tangent line is an approximation near the point of tangency. Let's first write down the equation of the tangent line to a curve f at the point C f of c? Well, that would be the point slope formula. Y minus f of c equals the slope f prime of c times x minus c. And you could simplify that if you wanted. You could write it as y equals f of c plus f prime of c times x minus c. That's the tangent line equation at x equals c. Okay, I'm going to introduce some notation now. Please don't panic. It's just a lot of little notation. First of all, delta x, we've seen that before, that's going to be x minus c. In other words, it's a small horizontal distance. Delta y, we've also seen before, it's the difference in the y values of our function. So it would be f of x minus f of c, where x is a nearby point. So that x could be called c plus delta x, couldn't it? It's near c. It's c plus some small distance. So that's the difference in the y values. F of c plus delta x minus f of c. And we see, pardon the pun, that delta y is approximately f prime of c delta x. Because look back at the equation for the tangent line. It was y minus f of c equals f prime of c delta x. X minus c is delta x. So delta y is approximately f prime of c delta x. That's basically like the derivative definition. If you were to move that delta x over to the left-hand side, you'd have delta y over delta x. That's approximately the derivative. The derivative equals that if you take the limit as delta x goes to 0. So this expression, f prime of c delta x, we call the differential with respect to y. So this is the definition. dy is defined to be f prime of c delta x. And they usually say delta x equals dx, and they get the definition that dy is f prime of c dx. So that's our definition of the differential of y, and dx is the differential of x, and it is a small horizontal distance. Let me show you a picture that puts all this together, and I think it'll make us more comfortable. Here's a picture of a curve, f of x, and I've indicated x equals c and f of c as one point on the curve, and I've drawn the tangent line at that point c comma f of c. Then I took a nearby point at a distance delta x from c, and I call that point x. So x is near c. It's the horizontal distance of delta x. And now go up and have x go up and bump into the curve. It hits the curve at f of x. Okay? So we have c hitting the curve at f of c, and the nearby point x hits the curve at f of x. Good. So who are our characters, delta y and dy? Again, delta x is the change in the x values, and you can think of that as being dx. dx and delta x are the same thing. It's just a notational thing. Delta y is the change in the y values. So it's f of x minus f of c. It's the change in the y values on the curve, on the function. Who is dy? Well, dy is an approximation of that change using the tangent line. Do you see how dy in this picture, it's a little bit smaller in this picture because my curve is concave upwards. But you can see that dy uses the tangent line to approximate that vertical distance. And if delta x is small, dy will be very close to delta y. That's what we call linearization. It's that simple, except that the notation is kind of like, eh. Okay, let me do a quick example of this skill. Let's take our old friend x squared, whose derivative is 2x, and ask for the linearization at c equals 2. So f of c is 4. F prime of c is also 4. And let's take a nearby point, say 2.01. That makes my delta x 2.01 minus 2, or 0.01. That's a small horizontal distance. What's delta y? That would be f of 2.01 minus f of 2. And if you plug that in, you get 4.0401 minus 4, which equals 0.0401. Now, what's dy? dy is the derivative at 2 times dx. So that's 4 times 0.01, and that's just 0.04. Miracle of miracles, those two numbers are close together. That's all we're saying here, that those numbers are close together, just with a lot of fancy notation. Here's a picture of that situation. There's 2, there's 2.01, there's 4 and 4.0401, and you see that the tangent line approximation gives a very good approximation of delta y. Good. Again, I admit this differentials topic has some complicated notation, but remember, it's just the tangent line approximation. Well, I'm very excited about the next couple of lectures. We know a lot about functions now and graphs. We're going to put it all together, and we're going to start solving some real-life problems. We're going to do what we call optimization. This is one of the first applications of calculus. We'll do some really fun examples, and I think you're going to enjoy the next 2 lectures. Thanks very much, and see you next time.